Hello everyone, this is our first lecture under the title Propositional Logic, Section 1.1. Introduction. What is discrete mathematics? Discrete mathematics is the branch of mathematics that deals with objects that can assume only distinct, separated values. The term discrete mathematics is always used in contrast with continuous mathematics, which has a lot of branches. So we have calculus, differential equations, we have linear algebra, we have many of these. So discrete mathematics is a branch of math in which the number encountered mostly are integers. Proposition. Definition. A proposition is a declarative sentence that is either true or false, but not both. Example of propositions: Los Angeles is the capital of California. Broadway is a street in New York City. 1 plus 1 is equal to 2. 5 plus 5 is equal to 20. The above statements are propositions. Proposition 2 and 3 are true, whereas 1 and 4 are false. Non-propositional statements. Example 2. Classify the following statements as declarative, interrogative, imperative, or exclamatory. 1. What time is it? 2. Multiply the following numbers, 12 and 13. 3. What a difficult exam. 4. 3x plus 1 equals 7. Statements 1 is interrogative, statement 2 is imperative, statement 3 is exclamatory, and statement 4 can be a declarative sentence if we assign a value for the variable x. Propositional variables. We use letters to denote propositional variables or statement variables. They are variables that represent propositions. Conventional letters used for propositional variables are P, Q, R, S, etc. The truth value of a proposition is either false, denoted by F, or true, denoted by T. Negation, or sometimes we use this symbol for negation. Definition. The negation of a proposition P is the statement not P, or it is not the case that P, written in symbol as negative P or P bar or P prime. The negation operator, negative, that is denoted this way, produces a new statement from a given statement. If P is the moon is round, then negative P is the moon is not round. Look at the truth table below. P, when we apply the negation, become negative P. T, when we apply the negation, become F. F, when we apply the negation operator, become T. Therefore, for every proposition P, the truth value of its negation is opposite of P. Conjunction and. Definition. For two statements P and Q, the conjunction of P and Q is the statement P and Q, denoted by symbol P, conjunction symbol Q. The truth table below shows a different combination of P and Q. Please take a look at it. In conclusion, the conjunction of P and Q is true when both P and Q are true and is false otherwise. Example: if P is the statement I am at school and Q is the statement it is raining, then P and Q is the statement I am at school and it is raining. Disjunction or definition. For two statements P and Q, the disjunction of P and Q is the statement P or Q, denoted by P or operator Q. Therefore, P or Q is true if at least one of the statement P and Q is true. Please see the truth table below. The use of the OR operator in disjunction operation correspond to one of the two ways the word OR is being used in English language, namely the inclusive OR. Example: if P is the statement I am at school and Q is the statement it is raining, then P or Q is the statement I am at school or it is raining. Exclusive OR, XOR. Definition: for two statements P and Q, the exclusive OR of P and Q is the statement P XOR Q, denoted by P XOR Q. In the table below, the truth table shows different combination of P XOR Q. The truth table above states that the proposition is true when exactly one of P and Q is true and is false otherwise. Conditional statements, if then. Definition: for two statements P and Q, the implication if P then Q is commonly read as if P then Q, and implication is also sometimes referred to as a conditional statement. The statement P in the implication if P then Q is the hypothesis of the statement, while Q is the conclusion. Example of conditional statements: if he gets a promotion, then we'll all go out for dinner. If he score a touchdown, then we'll win the game. If this jacket is on sale, then I'll buy it. If he complains one more time, then I will scream. Here we will discuss the truth table of implication. So now we can ask, when is the implication statement true? It's true if both P and Q are true. It's true if both P and Q are false. It's true if Q is true and P is false. It's false if P is true but Q is false. Logical jargon for the statement if P then Q. P can be called the hypothesis or antecedent or premise, while Q can be called the conclusion or consequent. Conditional statement. This is how we formulate conditional statement. If P, then Q. P only if Q. Q unless negative P. Q when P. Q whenever P. Q follows from P. P implies Q. Q if P. P is sufficiently for Q. Q is necessary for P. If then is extra confusing because it is not the same as programming if then or English if then. More confusion. In the following statement you will see a lot of confusion. For instance, the following implications are true. For instance, if P then Q is true, but it does not make any sense in English. For instance, say the following: if the moon is made of green cheese, this is false for sure, right? If the moon is made of green cheese, this is false for sure. Then I have more money than Bill Gates. That is also false. But this statement is all true. This the whole statement now is very true. Okay, again, if 1 plus 1 equals 3, okay, this is false for sure, then my grandmother is old. For sure, your grandmother must be old because she's a grandmother. So the whole statement here is true too. Why? Because here Q is true, so it's true according to the truth table. Two ways to avoid confusion. Do not think of if P then Q as if then statement. Instead, translate the statement into simpler logical connectives, usually using negative and negation, or using union, or using intersection, and so forth. By conditional statements, this is defined as the statement that states the following: P if and only if Q. The conditional statement is true when P and Q have the same truth values and is false otherwise. The truth values on the side for P and Q is true when both the conditional statements of if P then Q and if Q then P are true and is false otherwise. By conditional statement, there are some other common ways to express by conditional statements. Number 1, P is necessary and sufficient for Q. Number 2, if P then Q and conversely. Number 3, P if and only if Q. This is list of operators that we discussed so far, so please take a look at them. So we may use more than one operator at a time, and when we do so, we call this statement as compound proposition. The statement if P then Q is the same as the statement negative P union Q. And as you can see, the truth table here for both two statements produces the same result. There are many other ways of rewriting a statement. This is a chance to learn about converse, inverse, and contrapositive. So the statement number 1, if Q then P, the converse of this statement is the statement if P then Q. You see here we change, both P and Q changes position. Also, what is the inverse of a statement? The inverse of a statement, for instance, if negative P then negative Q, the inverse of that statement is if P then Q. You see here, these two statements pretty much are the same, except that we drop the negative. Okay, for statement number 3, when do we find a contrapositive statement? A contrapositive statement from the above statement, if negative Q then negative P. The contrapositive of that is the statement if P then Q, right? Introduction to number systems. We have decimal of base 10, we have binary of base 2, we have octal of base 8, we have hexadecimal of base 16. So we've been using this numbering system without knowing it on our daily life. Computer represent information using bits. A bit is a symbol with two possible values, two symbols, true and false, 0 and 1. The following are the references from which we obtain the information in front of you.